welcome YouTube to Mr. Robinson's Q&A Power Hour, where here in Integrated Math 2 related questions and answers, we are going to be looking at things regarding angles. I'm trying to think if we did anything with segments. No, it's just angles. Angles, vertical angles, linear pairs, adjacent, complementary, supplementary, things with parallel lines. That means corresponding angles, alternate interior and exterior. Same side, interior and exterior. Questions along those lines, I assume, is going to be a part of this nature here. I'm trying to think if there's any other kinds of questions that can be asked. I haven't looked at the questions yet. I'm going to look at them with you right now. I'm just going to go ahead and get started. So let's see. Let's begin right here. And our first question asks, how do you find the different angle measures in figures? Well, it depends. If it's something like we haven't done in class, if you're talking about if you don't know any angles whatsoever and there's no way you can have them given, like you don't know something's a right angle, you don't know two things are a linear pair, things like that, or triangles are isosceles, you can use something called a protractor. And again, not something we're doing in class right now as we're only distance learning, but a protractor would look like this. Or using a protractor at least. And I don't know if this is what you're talking about. Where are the math buttons? I think it's here. Yes. So a protractor is like this tool right here. Let's make it a little smaller. And what this thing does, if I ever wanted to find an angle, let's say I want to find out how big this angle measure is right here. What I do is I take this thing. This can be a physical object. You can actually use this thing like in class. It's a transparent piece of something where you lay this middle part right here onto the vertex of the angle like that. And then what I can do is really just look at, I'm going to rough it right now. If this is 0 degrees right here, then 10, 20, 30, 40, 50, 60. This goes all the way to about 132 degrees or something like that. Now, I can actually, with this tool, I can drag it over into there and see exactly, that's as exact as I can get, but how many degrees I can get with there and kind of take a snapshot. So 133 degrees would be that angle. So you actually use a protractor and go from one arm on one end there, see where it goes in the middle here, and it goes on black, and then I look up on black here and kind of see what angle it's hitting. And again, it wasn't perfect. Maybe that's even better. I don't know. 133, 132 degrees. That's what a protractor is good for. That's what we can do for actual physical things. However, some of the things we're talking about, it's less about what the actual angle measure is, because we don't assume something's drawn to scale, or they might want to manipulate numbers as they see fit. So in one problem, it's 45 degrees. In the next problem, it's 85 degrees. Who knows? Because sometimes they want to do that, so they say, don't assume it's drawn to scale. Go by the other things mentioned, such as these are vertical angles, or these lines are parallel, to do that. And then I'm sure other questions will be asked here, but how do you find the different angle measures in figures? It helps to know angle pair names and their actual mathematical relationships. In several different angle pair relationship names, angles will either, angles will either be equal to each other. So you set those two angles equal because their angles are congruent, so their measures will be set equal. The angles may be complementary, which means those angles add to 90 degrees. Or those angles may be supplementary, which means they add to 180 degrees. And every so often we get to set an equation based off that. So the knowledge of, say, a linear pair adding to 180 degrees is how you can help find the measures of angles, assuming you know something about them. Maybe you know that one of them is 45 degrees, and then the other has to have an x in it, so you set it equal to x. But it sounds like you're not even getting that deep as far as the x stuff. But you can only find things based on understanding their relationships. And like I said, I think people will ask more questions beyond that little part that you're asking. But knowing if two angles are equal, or knowing if they add to, say, 90 or 180, or when we get into interior angles and we talk about them adding to 360 or 540, just different things helps you by knowing those relationships themselves. Okay, and then otherwise the protractor is of use. All right, the next question says, if there is more than one transversal, can an angle still correspond to another angle that is on the same side of the intersecting lines, but on another transversal? My guess is you're asking, well, the answer is no, just by the angle name relationship. But just to clarify, I assume you're talking about, so say we have two, this is just to begin with, say we have two parallel lines cut by a transversal like this, and then we say, okay, these are corresponding angles right here. When these lines are parallel, corresponding angles are congruent. I don't even know if you asked about congruent. I think you just asked if they correspond, but let's just assume they're parallel to make this easier. So two parallel lines corresponding angles are congruent because they share this transversal that I'll make in blue. So I have this blue transversal for these two parallel lines. Well, what if there was another transversal here that was, say, green? And maybe you're asking this, and let's just to make this easier, let's say that these two lines are parallel as well. The blue and the green lines are also parallel. Now maybe you're asking something like, is this angle right here corresponding to, say, this angle right here? And the better argument I can make right now is because I have these two lines parallel, that would, I guess, make these congruent. And I can kind of prove that by using a transitive property. If by these two lines being parallel, these two are congruent. And if by these two lines being parallel across this transversal that these two are congruent, because those are also corresponding angles, then these two must also be congruent. And therefore, they might be corresponding angles? Not necessarily, no. Remember, corresponding angles has to exist by the angles formed by a single transversal. This angle right here and this angle right here do not share any line whatsoever. Therefore, they are not part of the same transversal anywhere. This has this blue line and this bottom black line, and this has the green line and the upper black line. So no, these two angles do not correspond. Now, they do share, and this is something I'm going to start mentioning, I think, in class here on out. They do have a mutual friend. They do have a mutual friend, and through that mutual friend, you can say these are corresponding angles that are congruent, these are corresponding angles that are congruent. Therefore, these two are congruent just by that relationship there. So that's something that you can make happen through the mutual friend, but you need to use that mutual friend to talk about these two parallel lines cut by a transversal, and then these two parallel lines, blue and green, cut by the single transversal. So they need to share a transversal to have any of those certain names. That doesn't necessarily mean they won't have any angle relationships together. But of course, if these lines were not parallel and look something like that, then these angles are no longer congruent for the same reason that, of course, these two angles are no longer congruent. Just because they're corresponding, the two lines are no longer parallel. Now, that doesn't make these two non-corresponding. They're still corresponding. But I hope that does answer the question. They need to have the same transversal to have any of those names that we're referring to there, because that's the whole key. Otherwise, we're just sniffing around any object, and it doesn't really work that way. Okay, next question is, are same-side interior angles congruent or supplementary? Well, when lines are parallel, same-side interior angles are supplementary. Both of the same sides, the interiors and exteriors, are supplementary when lines are parallel. The alternate exterior and interiors are congruent when the lines are parallel, and the corresponding angles are also congruent when the lines are parallel. Vertical angles are congruent, linear pairs are supplementary as well. One last thing I want to note here, and I'm sure I've said this in class already, is that, you can make this obvious enough for yourself. I'm not going to get deep into this. You can make this obvious enough for yourself. Let's just get an obvious look of one to really talk about what's an acute angle, what's an obtuse angle. This is clearly a very acute angle here, guys, and this is clearly a very obtuse angle. I hope you agree. Very acute versus very obtuse. Now assume these lines are parallel here. These same-side interior angles right here, and this is an example of a same-side interior angle pair, that is impossible for those to be congruent. One is so acute looking and one is so obtuse looking. That is impossible for those to be congruent. And I hope that you can recognize that the corresponding angles here are congruent. So these two might be congruent there, and these two make a linear pair. So these two adding to 180, a very acute plus very obtuse adding to 180, would make sense that these two add to 180 as well. You could do it with any of the other ones, guys. If the lines do look parallel enough for you to say something looks acute versus something looks obtuse, then you can tell that those couldn't be congruent in the first place anyway. So very clear that those will be that. And we put it in our notes as well. I don't know if I can give, no offense, I don't know if I can give full credit for a question like that, because it's not because it's an easy thing to answer. It's because we've easily talked about this a lot before. And that's something that it's one small question in class and we go ahead and answer that. And it's been in a bunch of notes and you've been quizzed on it as well. Actually, yeah, you've been quizzed on it as well, so it's just a huge thing. I want you guys to explore the things more here regarding this. Okay, what does theorem mean? A theorem is a true statement that can be proved. It can be proved. And not that it can be proved, it has been proved. So the Pythagorean theorem, there is a proof that the sum of the squares of the two legs of a right triangle equals the square of the hypotenuse. I'm not going to dive into the proof, but if we ever do together, it looks something like this. They have a square, and then I don't know how small or large I can draw this square to make this work here. There's another square within that's rotated. Oh shoot, let me make this a little smaller. There's another square in here that's rotated, and in here we kind of make right triangles out of this business here. So if you guys can imagine here, we have, hang on, I'm not gonna prove the Pythagorean theorem here. The Pythagorean theorem, guys, is your a squared plus b squared equals c squared. So, all right, pretend like, yeah, that's pretty good. All right, within here, we actually, we have some right triangles. Let me just draw one out so you can see it here. But they use the Pythagorean theorem proof out of the knowledge that you have two squares drawn within here. Square here meaning all right angles and all equal sides, and you can call any of the side lengths of this one here C. And then say that this is a length A and this is a length B right there. They can do certain things in here, and I'll show it to you sometime if we want to dive into the proof. I'll show you the proof for the Pythagorean theorem that the sum of the squares of these two things is squares of the third. And the way that the square thing in here works is if this is A, then this is also A. And then if this is B, then this is also B. And then there's another A and a B and another A and a B. And it kind of works off that notion to kind of help find relationships of the area of this inside square with the areas of these parts right here. And it does certain things like that to really help come into play with the a squared plus b squared equals c squared stuff. So anyway, the way that proofs work, and well, actually, let's see, that's not what you're asking, but this helped prove that a squared plus b squared equals c squared, that for any right triangle, the sum of the squares of your two legs equals the square of the hypotenuse. So this helps bring that into light. Let me just write the theorem in case you don't know it. And it makes it indisputable, and that's what a theorem is. There are other words called a postulate. A postulate is a statement that we assume to be true. It's something that is so basic in nature, such as parallel lines will never intersect. Actually, that's more of an axiom, but that's postulates and axioms I almost consider to be one the same. It's a statement that we kind of assume to be true. There's nothing you have to prove to it, because there's absolutely nothing that can ever upset it or offset it, that just by definition alone it makes the nature of what we're talking about hold true. And then there's something called like properties, for example. Properties are true statements based on math being what it is, that the way that addition works and multiplication works and stuff like that, that the nature of properties have to exist in such a way. I mean, so there are different things like that. But a theorem, if you have a theorem, it means it has been proven to be true. And the cool thing is we get to then use those theorems to do other proofs down the line. Anyway, Pythagorean theorem is just one instance of it. Let's look at the next question. Why is it that there is m sometimes and there isn't while writing an angle? Well, that's a good question. The idea behind this, and let's draw something here. The idea behind the m, or more so not the m, let's just call this angle A, just to be quick and easy about it. So this is angle A here. Okay, now I just said this is angle A. Guys, you see this angle here? This angle is called angle A. Physically, it's called angle A. Whenever I say angle A, I'm saying look at this right here. I'm doing the Patrick, look at it, look at it, look at it. I'm saying, anytime I use this, I'm saying, guys, look at this. The physical object. You see this? This is what I'm talking about. I don't care how many degrees it is right now. I care what it looks like. In terms of size, in terms of shape. Orientation and color don't matter, so by that I mean that this thing could be rotated like this, and it could be green. That doesn't matter, because this angle A could be congruent to something else as long as it is equal in size and shape, meaning I could change the color to look like it, or I could map one onto the other and make it match exactly. So that is what angle A is. Measure of angle A, m angle A, is in reference not to the angle, but the value of the degree of the angle associated with it. Let's say that the measure of angle A is 35 degrees. That's what this is. The measure of angle A is 35 degrees. That is the value tied in with this. Measure of angle A does not have a physical component to it. You can look at where it exists so you can find the measure of the angle or something like that, but the measure of angle A has a number. This is an abstract thought in terms of the value assigned to it. Angle A is the physical thing that we're talking about, the actual angle. So you'll never see me say something like angle A plus, let's say there's another angle B equals 180 degrees. That doesn't make any sense within the confines of geometry, the things we read. You're talking about adding an angle to another angle. We don't do that. We add their measures, though, because that's a mathematical thing. We take numbers and add them, and if they add to 180, okay, that's great. We can do that, and measure of angle A is 35, And you can solve measure of angle B by doing that. So the same holds true when we do segments, and down the line we are going to be doing more things on segments. You've seen a couple now, although I have not called attention to the fact that this is happening. Let's say I do have a segment that is AB. So this goes from A to B right here. Same thing here. When I write AB with a bar above it, I'm saying, guys, look at the segment itself. Look at this thing. Do you see it? There it is. When I write AB without a bar, that means the length of AB. This means length of AB. So if it does actually have a length, because it is a segment, or length of segment AB. So if it actually does have a length, like say it's 5, then I would say that AB equals 5. And this is the number that ties in with it. So the same kind of thing. That's how angles work, with the little m in front says the measure of the angle, and then the angle itself is the physical thing. Same with segments there. I hope that clears that up. All right, good question though. All right, let's look at the next question here. How do we use proofs in real life? Well, we're probably not going to do, you're probably not going to do mathematical proofs in real life, but how do we use proofs in the math class to build up deductive reasoning, logic and reasoning, I should say, and deduce things through use of repeated patterns and make use of structure? You know, you're basically working your brain molecules to work that way, and if you're doing that in math, then I guess that can also work in real life. Deductive reasoning, and find things that are indisputable evidence to make a valid statement about something that you can prove. All right, think about, this is what they do. It's not necessarily how to use proofs. A proof is just a way of proving something. So what you're really asking is, how do we prove something in real life? And the answer is, find indisputable evidence to say that no one could ever counter that in any sort of way whatsoever. And, you can't prove by example. And this isn't just in math, this is in real life as well. You can't prove by example. I like to use a fire truck example a lot. I say, look at that fire truck, it's red. Look at that fire truck, it's red. You see that fire truck right there, it's red. I can name 2,000 red fire trucks in a row. I'm sure I've done that at some point in my life. The last 2,000 fire trucks I've seen may have all been red, or the first 2,000, or the middle 2,000. There might have been 2,000 consecutive fire trucks I've seen that are red. So I might make a conjecture, I might believe that therefore all fire trucks are red, but I have not proven it. What would I have to do to prove it? I'd have to probably find the manufacturer of fire trucks and go into their warehouse and find out that the only color of any sort of primer and paint and stuff and coat that they use is only red, and that, maybe that's my proof, that I go to every single one of those and determine that they don't use any other colors for it. Granted, I know I've seen green fire trucks before. I think I've probably seen white fire trucks before, and all different colors, but for the most part, they're all red. But I haven't proved by example. In fact, someone could disprove by counterexample. The moment you see a green fire truck, my proof's no longer proof. So anyway, I can't prove by example that something works. You have to find indisputable evidence of that. How do you use proofs in real life? In real life, you prove something not by example, but by evidence that backs it up, that says there's no way to dispute it in any other sense. I don't know if I answered that for you. However, why would we use proofs in math? Which, by the way, we haven't really talked about proofs yet. We're going to start that going into the next thing, and I'm sure there are going to be more questions asked in the next Q&A Power Hour video on this. But how do we use proofs in math? By deductive reasoning and logic, by looking for and making use of structure, and by seeking repeated patterns in something. And then that can back it up. Just like the Pythagorean theorem proof. There's no way to go outside of that, what you have there. All right, let's look at the next question here. What is the difference between an angle bisector and a perpendicular bisector? Well, I don't know if we've done angle bisectors yet, but a perpendicular, so you might not even want to ask perpendicular bisector yet, though I will say it. A perpendicular bisector is a specific kind of segment bisector. So that's something that goes through the midpoint of a segment, meaning you have two congruent parts of your segment. So a perpendicular bisector, or any segment bisector, looks like, if I have a segment right here, my bisector might go right through the midpoint of the segment right there. So that means that this part is congruent to this part right here, even if it's perpendicular. So a perpendicular bisector does the same thing. It goes right through the midpoint, say that is the midpoint, and then it gets those two parts congruent. It's only perpendicular because it makes a right angle. However, well, actually, I guess it acts as an angle bisector at the same time, but that's for a different reason. Its goal is that as it makes 90 degrees right here, it also had divided its two congruent parts. So a perpendicular bisector is a specific type of segment bisector. An angle bisector, I guess this, technically, I'll go back to this. Perpendicular bisectors do work as angle bisectors, but for different reasons. An angle bisector is a line, ray, or segment that goes through the middle of an angle in such a way that it divides the angle into two congruent parts. So let's say it's something along the lines of like, I'm trying to get as best as I can, maybe something like that. So this thing here is an angle bisector because it makes this part congruent to this part right here. So it goes right through the middle of those and it makes these two angles here equal. Now the reason why this can also technically act as an angle bisector is because if it goes through a segment, I guess a segment could be considered as a straight angle. So this angle here, let's call it angle ABC. The measure of angle ABC is indeed 180 degrees because it's a straight angle, I guess. And then when I did this segment bisector right here, the perpendicular bisector DB, now I know that something like the measure of angle ABD is 90 degrees. So I guess it technically bisected the angle as well, but for different reason. This B probably didn't exist before you created the bisector, and we're probably not looking at this as much of a straight angle as anything else, but I guess it worked. So what's the difference here? One is really for segments, one is for angles. We haven't really done angle bisectors yet, but an angle bisector divides the angle into two congruent parts. Perpendicular bisector or any segment bisector divides a segment into two congruent parts. So there you go. All right, let's take a look at the next question here. Why do angles sometimes not all add up with the theorems correctly? I don't know what you mean. If you're talking about how like same side interior angles aren't always supplementary, it's just by nature, but it's not that, well, let's see. The theorem says they're always supplementary because it starts with a very specific condition, if the lines are parallel. So if you're asking why don't they always add up the theorems, because sometimes the theorem's not being applied, you first need to meet the hypothetical condition that the lines are parallel before that holds true. It's just by nature, I mean, there are proofs to these as well, but it's by nature that alternate interior angles are congruent or same side exterior add to 180 or something like that. Because the lines are parallel, it's by nature that those actually hold true, using things like vertical angles, linear pairs, corresponding angles, things like that to talk about it. That's where the proofs come into play. But I mean, if you're asking why, I mean, a different question could be, why do we still call them same side interior angles if they're not congruent? I don't know. I guess just so that way we can use that to reference. I actually don't know. There's actually, because their relationship doesn't hold true anymore, it's kind of weird to bring it up. But yeah, let's say I have two lines totally non-parallel and they're cut by a transversal here. These two same side interior angles clearly don't add to 180 degrees if for no other reason than both of these, hang on, let me make it even more acute. Both of these angles are actually acute. How could two angles that are less than 90 add to make 180 if two angles that are 90 add to 180? So it's clear that these two won't add to 180 right here because the lines aren't parallel. I mean, you need the lines to be parallel to make it happen. And I mean, I don't know why we still call it same side interior. I mean, I know that the relationship is as such, but I don't know why that name matters anymore in that way. So I don't really know if that was the question that you're asking. I don't really know if I answered it in that way as well. But basically, you need to first meet the if part, right? You need to be a triangle to have three sides. You know, if you say if it's a square, why isn't it now? Why doesn't it have three sides? Well, because it's not a triangle. You know, you need to make sure that you first meet the initial condition for it to actually work out. So we need those lines to be parallel for that to work. I don't really know if that's what you're asking, but that's what I'm going with. Okay, are alternate interior angles always corresponding? They're never corresponding. They're always congruent though. They're always congruent when lines are parallel. No, alternate interior angles are not the same as corresponding angles. Make sure that you know the vocab with that. If you meant to say congruent, they're only congruent when lines are parallel. And that kind of talks about this right here as well. You need to first meet the condition that lines are parallel for them to be congruent. Now, corresponding angles are always congruent, like alternate interior angles are always congruent, provided that those lines that are cut by the transversal are parallel. Okay, the next question. When proving lines are parallel, how would you show that the lines are perpendicular to the same line? Are we doing that yet? I don't even know if we are actually doing that. There are a few theorems. I'll say them out loud. I don't think they're going to matter to you, and I don't know if this is what they're asking. But there are a few theorems that come into play at some point that says, I think there are 3 different ones. So the first one, which is not being asked about right here, but it still falls in the same vein because it has to do with parallel lines as much as perpendicular lines, that says if there are 2 parallel lines, two pairs of parallel lines, so this pair and this pair here, if there are 2 pairs of parallel lines that are parallel to the same line, then those 2 lines are parallel to each other. What that means is if I have these 2 lines that are parallel and these 2 lines are parallel and they're both parallel to that same line together, then these 2 must be parallel to each other as well. There's a theorem to that, which, again, statement that can be proved. So there's something within a proof. Another one is if you have, and I'll read their question after, but there's 2 that are kind of the same. If you have 2 this is probably the one that they're asking about. If you have 2 parallel lines where one line is perpendicular to another, to a third line, then the other line of the parallel. I'm not saying the theorem as cleanly as it could, but if I have 2 parallel lines, if one of two parallel lines is perpendicular to a third line, then the other line is also perpendicular to it. That's kind of a statement. And then the last one is a line that's perpendicular, and I don't know if I'm saying it correctly as well, but this is the idea. A line that's perpendicular, if one of 2 perpendicular lines is perpendicular to a third line, then 2 of those lines are parallel. So kind of something like that. It's just kind of weird. Anyway, so 3 different theorems in play here. Now, that doesn't yet answer the question. So the question, I think, has to do with this one here. Let's see what the question was. When proving lines are parallel... Oh, no, you are asking about this one here. When proving lines are parallel, how would you show that the lines are perpendicular to the same line? Well, here's what would happen. You'd have to know that one of these 2 lines are perpendicular to begin with. Okay? You'd have to know one's perpendicular to begin with. And then the second one, well, I guess eventually you'd have to know that the second one can be as well. So in a nutshell, you have, say, corresponding angles. Now, corresponding angles that are congruent means that these lines will be parallel. That's really the idea of the proof. So I guess you'd have to know 2 lines are perpendicular. You'd have to somehow deduce, or they'd have to tell you that this line is perpendicular here. And once you have corresponding angles that are congruent, that'll therefore make the lines parallel. That's the converse of the corresponding angles theorem. You could also do it with, these ones too. You could do converse of the alternate interior angles, things like that. But you can always make them into corresponding angles to make it happen. So I don't know. You're going to have to use the converse of the corresponding angles theorem to make it happen. And you're going to have to be given enough information that these 2 lines are perpendicular and they make right angles, say, to make that actually happen. I don't know. Anyway, these are 3 theorems that do come into play at some point. I don't know when. They should have done it in 14.4. I don't really know if they brought it up. All right, here we go. When labeling the types of angles, how do you do that when you have to do it with letter? In Edulastic, we had to say if they are alternate interior angles or such. How do you do that with 3 letters? Naming an angle with 3 letters is simply done by using 2 letters that are on the arms of your angle and the letter that makes the vertex of your angle. Let's make it like the Edulastic stuff. So 2 parallel lines cut by a transversal right here. And let's do our ABCs here, guys. We have A, B, C, D, E, F, G, H. Now, we had an opener that kind of started off this chapter in the same way. A 3-letter angle name is designed by having a letter that's on the arm of the angle that you're referring to, another letter that's on the arm, another arm that makes the angle, and then the vertex where the angle is kind of located at right there. So if I wanted to do this angle right here, I could call this angle ABC because I start on this arm that has A on it, and then it goes to B, that's the vertex, and then it goes to C afterward right here. If you want to talk about some alternate interior angles, let's look at these 2 right here. Let's look at this one. Whoops. Let's look at, say, this one right here. So I can call that angle DBE because it goes from D and then to B as the vertex, and then it goes to E right there. You know what? I could also call this DBH. I could also call this DBH because H lies on the same arm as E does right here. It does go all the way down. Remember, the angle is just this part right here, but the arms help describe and show what makes the angle in and of itself. But that is the angle right there. And I could call it DBH like that because the arm extends all the way down to H in the same kind of way as it does to E. Doesn't matter, it's still the same angle regardless. Now I could also reverse the letter order. I could call this HBD. How about that? I could call it HBD, or I could call it EBD as well. Right? Those are actually very possible to happen. Likewise, here's the alternate interior angle with it right here, like BEF. BEF, angle BEF. Or, of course, I could call it AEF, because I could have started up here, or I could reverse the letters there. You have to use 3 letters. You have to use 3 letters, and the 3 letters have to go in such a way that it goes from an arm to the vertex to another arm that makes the angle. And that's the extent of it. That's the extent to which I can even go talking about it there. But 2 arms and the vertex that's the angle is made of from those 2 arms. Points on the arms, I should say. All right, let's see how many questions I have left here. Not very many. Can you prove that lines are parallel using an equation? Can you prove lines are parallel? Well, sort of. If you set things, we've sort of done it. If they say, what value of x would these 2 angles have to be to prove the lines are parallel? And it has to do with knowing what kind of angle relationship name you have. If these are alternate interior angles that we're looking at right here, boom and boom, we have to set those equal to each other. And if we get the certain x that matches both of those, if it's the same x there or whatever, then yeah, you have alternate interior angles, because if the angles are congruent, then the lines are parallel. Or if same side exterior angles are supplementary, you can say those 2 add to 180. And if they do properly add to 180, well, then the lines are parallel, because we're using the converse of the theorems in that way. So yeah, we've done that. We did that in section, I'm not thinking my sections right. Section, I think 14.3. Check section 14.3 when we were doing stuff like that, and that definitely holds true. Okay, when are we having our Unit 6 test? Well, that's an interesting thought, because it used to be April 22nd, but the thought now is that we are going to be doing like a Unit 6A test and a Unit 6B test. So we'll do stuff based on 14.1 through 14.4 first, which changes things. That's a good question. Let me pull up my pacing guide and see when our Mod 14 stuff runs out. And then we got to review. I'll have to look at this sideways. So it says Mod 14 review on the 11th. Now, that won't necessarily hold true in certain ways here, because I'm going to go back and do some proofs with you guys. I'm guessing at the end of next week, so on the 18th, I'll announce this in class, on March 18th is probably when we will exam for Unit 6, and then we'll dive into Mod 15 and do stuff there. That's going to be my guess. That's going to be my guess. It's not a content-based question, though. All right, how do you find a non-given angle when the other angles are not congruent to the one asked? Well, it depends. They could be supplementary or complementary as well, right? So you might not know they're congruent. They might not be congruent at all. They might just be supplementary angles. So if they're supplementary, just by nature of knowing they're a linear pair, then you add them up and set them equal to 180. Or if they're complementary, you add them up and set them equal to 90. Supplementary means that those 2 angles could form to make a straight angle if you put them together. And complementary means those 2 angles could make a right angle if you form to put them together. They add to 90 degrees. So how do you find a non? So there are those ones there. You could just literally have a linear pair as well. I'm trying to do ones that are supplementary or complementary, because those are the ones that we're kind of going to know right now. Eventually, we're going to do more things with adjacent angles right here. So I could do something like this. If I knew, let me kind of write this one out. So this is neither complementary nor supplementary, right? But maybe I have a split right here, and let's call this thing A, B, C, and D right there. So let's say that we knew that the measure of angle ABC was 3x plus 20 degrees, and then the measure of angle ABD was 5x plus 25 degrees or something, and I say find the measure of angle, find the measure of angle CBD, for example. So you know how much this is right here, you know how much this is right here, and we're trying to find out how much this is right here. You know what I mean? Nothing here is congruent, but the angle addition postulate says I can add this angle with this angle to make the whole thing. Now we know the whole thing, and we know one of those when we need to find the last one, so we'll do a subtraction through it. So it's not always things will be congruent. If they add to something as well, and we know enough information about it, such as these angles are adjacent, so this plus this equals the whole thing, you know, we can do something like that. And I'm not going to solve this one right now. And actually, there's not enough to solve for. I probably shouldn't have used the x's. I should just say, okay, 20 and 25 degrees. You know, find CBD. I guess, okay, if this is 20 and the whole thing's 25, then this little part is 5. 20 plus 5 is 25. So you can do things like that. And of course, if you know same side interior angles are supplementary when lines are parallel, you can set those equal to 180 when you add them. Kind of things like that. All right, there are a bunch of different things there. They don't always have to be congruent. If they're not congruent, then they might be supplementary, complementary, or they add to something that we do know. All right, 2 more questions here. Can some angles still be congruent when the lines are not parallel? Sure. Well, hold on. I mean, sure, vertical angles can be congruent, and sure, other angles can just be marked congruent, all depending. You can even have same side interior angles maybe be congruent if they're right angles, but that's not the point. I mean, sure, some angles can be congruent. However, you cannot have congruent angles if, like, you can't have congruent alternate interior angles if the lines are not parallel. So if I have, wait, can some angles still be congruent? So here, if I have this look, clearly those lines aren't parallel. I didn't mark them parallel. And we're asking, are these alternate interior angles here congruent? No. Once the lines aren't parallel, these alternate interior angles can't be congruent. One comes with the other. One has to come with the other for that to work. If you're talking about ones that are congruent when lines are parallel, they are not congruent when lines are not parallel. So that I should probably give different arc marks here. Now, vertical angles are always congruent whether or not lines are parallel, because vertical angles has nothing to do with parallel lines. Vertical angles only has to do with these 2 lines here. Those are just intersecting. So those are still congruent, and those will still remain congruent even when these 2 lines aren't parallel. I hope that answers it. But yeah, alternate interior or corresponding and stuff, those are a one-to-one relationship. Only when lines are parallel are those congruent, and only when those are congruent are when lines are parallel. That's the biconditional thing that happens. Okay, and the last question asks, what is the difference between a linear pair and supplementary angles? Well, a linear pair is a specific kind of supplementary angles. A linear pair is a supplementary angle pair, and it's an adjacent supplementary angle pair. So this is a linear pair right here, these 2 angles, because they're right next to each other, they're adjacent, and they form to make a straight angle. Yes, they add to 180. That's just part of the definition of linear pair there. They are a specific type of supplementary angle pair. Just remember that angles do not have to be adjacent to be supplementary. They only have to be adjacent to be linear, a linear pair. So if I have another 2 sets of angles, one right here and say one right here, and maybe you know that they are supplementary, like maybe this plus this, the measures add to 180 degrees, even though that doesn't look quite right. They're still supplementary just because they add to 180. They don't have to be adjacent to do that. It's like you asking me, and I'm not making your question, oh gosh, what's the word? I'm not trying to like downsize your question in any sort of way or downplay it, but it's like asking me what's the difference between a Honda and a car. Well, a Honda is a specific type of car, right? So there's no different. Well, there is a difference. It's a specific type of car where something has to occur to make it a Honda. But all Hondas are cars. Well, not all Hondas are cars. They could be motorcycles and stuff as well. Just pretend like we're just talking about Honda cars. So anyway, I'm just trying to be specific in that kind of way. All right, so that is it. That's what that thing means here. I hope that all that stuff makes sense. That'll do it for me here. This is Mr. Robinson, and cut off the power hour a lot shorter today. That is good. Thank you, and I'm going to be recording another video 2 Fridays from now. I hope you stay tuned. Take care.